Hello everyone, welcome to my channel. I am Balaji Chandrasekharan. Today I will be discussing the solid design principles. I have used the Java language to showcase some of the examples to apply this in solid principles. In general, we can apply the solid design principles to any of the object-oriented languages. The solid principles are a set of 5 design principles for writing well-structured, maintainable, and scalable object-oriented software. These principles were introduced by Robert C. Martin, also known as Uncle Bob. These principles aim to make software designs more understandable, flexible, and maintainable. Here are these 5 principles: the single responsibility principle, SRB, the open closed principle, OCP, Liskov substitution principle, LSB, interface segregation principle, ISB, the dependency inversion principle, DIP. Here is a brief overview of each principle. The single responsibility principle SRB is the first of the solid design principles. It states that a class should have only one reason to change, meaning it should have a single responsibility. In other words, a class should encapsulate a single well-defined piece of functionality. When a class has multiple responsibilities, it becomes tightly coupled to different parts of your application. This makes it more challenging to maintain and test. If one responsibility changes, it can affect the entire class, potentially introducing bugs or requiring changes in unrelated areas. This makes it more challenging to maintain and test. In this example, the report class is responsible for generating a report, saving it to a file, and sending it by email. If any of these responsibilities change, example, the report format changes, the file storage mechanism changes, or the email service changes, the report class needs to be modified, which so violates the single responsibility principle. Since the report class is doing multiple responsibilities, making the code maintenance and test challenging. To adhere to the single responsibility principle, I am splitting the responsibilities into separate classes. Each class now has a single responsibility. The report generator class is responsible for generating the reports. The file manager class takes care of saving the reports to files, and the email service class takes the responsibility of sending the reports by email. This separation makes the code easier to understand, maintain, and test. The open close principle states that the software entities such as classes, modules, and functions should be open for extension but closed for modification. This means that you should be able to extend the behavior of a class without modifying its source code. This principle encourages the uses of abstraction and polymorphism to achieve flexibility and maintainability. Instead of modifying an existing class to add new functionality, you should create a new class that extends the existing one or uses interfaces to provide additional behavior. In the given example, the calculate area method of the shape class directly checks for different shape types and performs the calculation accordingly. If a new shape is added, the shape class needs to be modified, which violates the open close principle. To adhere to the open close principle, we need to use the polymorphism and abstraction. By introducing an interface shape and implementing its concrete shape classes like rectangle and circle, we make the shape class open for extension, adding new shapes by creating the new classes, but closed for modification. That is, the existing code in shape class doesn't need to change when new shapes are added. The list of substitution principle states that the objects of a superclass should be replaceable with the objects of a subclass without affecting the correctness of the program. In other words, the derived classes must be substitutable for their base classes without altering the correctness of the program. This principle ensures that the inheritance hierarchies are well designed and that polymorphism works correctly. In the given example, we have a superclass bird with a method fly representing the flying behavior. However, when we create a subclass ostrich that extends the bird class, we violate this Liskov substitution principle because an ostrich is a type of bird that cannot fly. By inheriting the fly method from the superclass, the ostrich class is forced to have a method that represents the flying behavior, even though ostriches cannot fly. This violates the principles that objects of a superclass should be substitutable with the objects of a subclass without affecting the correctness of the program. In this example, we adhere to the Liskov substitution principle by using interfaces and ensuring that subclasses provide appropriate implementation for methods. We define an interface flyable with the method fly representing the flyable behavior. The eagle and sparrow classes implement the flyable interface and provides their own implementations of the fly method. This allows each subclass to represent its flying behavior accurately. If a class does not fly, it does not need to implement the flyable interface, avoiding the issue of having a method that represents behavior the object cannot perform. Thus, the Liskov substitution principle is adhered to in the example by using interfaces to define contracts for behavior and ensuring that the subclasses provide appropriate implementations without being forced to inherit behavior that does not apply to them. The interface segregation principle suggests that the clients should not be forced to depend on interfaces they do not use. This principle states that the classes or interfaces should be fine-grained and client-specific rather than monolithic. It encourages creating smaller, more specific interfaces to avoid forcing clients to implement methods that they do need. In this example, the document interface contains methods for opening, closing, saving, and printing a document. However, the printer class, which implements the document interface, is forced to provide implementations for all the methods, even though it only needs to implement the print method. This violates the interface segregation principle because the clients of the printer class are forced to depend on methods they do not use, leading to unnecessary coupling and potentially confusing behavior. So I alter the code in such a way to adhere to the interface segregation principle. In this example, we adhere to the interface segregation principle by splitting the document interface into smaller, more focused interfaces that is printable and savable. Each interface defines a single responsibility here. The printable interface for printing the documents and the savable interface for saving the documents. The printer class now only implements the printable interface, providing a clear separation of concerns. Clients of the printer class are no longer forced to depend on methods that they do not use, leading to better code organization and reducing coupling. This adheres to the interface segregation principle by ensuring that the interfaces are fine-grained and client-specific rather than monolithic. The dependency inversion principle suggests that the high-level modules should not depend on low-level modules. Both should depend on abstractions. This principle promotes loosely coupling between classes or modules and makes the code more flexible and maintainable. Let us consider a Java class that violates the dependency inversion principle. In this example, the user service class directly depends on email service class, making it hard to replace or test user service independently. To adhere to the dependency inversion principle, we can introduce an abstraction that is an interface and inject as dependencies. Now, the user service class depends on the notification service interface instead of the concrete email service class, making it easier to replace email service with another implementation. Example, it can be SMS notification service or push notification service. It also helps to test the user service independently. These examples demonstrates how to apply each solid principle in Java with detailed explanations and code samples. Applying these principles can lead to more maintainable, flexible, and scalable software systems. Thank you for watching my video.